In this video, we discuss Euler's method, which is a numerical method for approximating the solution of an initial value problem. That's a differential equation subject to some initial conditions. Now here we're dealing with first order ODEs subject to some initial condition that looks like this. Now, typically the way we would handle this IVP is we would solve the differential equation using one of these methods that we've previously studied. If it's separable, we know how to solve that. If it's first order linear, we can multiply by an integrating factor. If the differential equation is homogeneous polar, we can write the first derivative as a function of y over x or x over y, and then we can make a substitution. And then through that substitution, the resulting differential equation will be separable, and then we can back substitute to get an implicit solution. We know how to solve Bernoulli differential equations by making a substitution. After the substitution, the differential equation becomes linear. You solve the linear equation and then you back substitute to get to the solution of the original problem. And then we said if the differential equation is exact, meaning if one side of the equation is the total differential of some function f of x, y, the solution of the differential equation turns out to be a level curve of that function of two variables. And we can find that level curve through a process of anti-differentiation and matching. Now, it's possible you look at this differential equation and none of that works. If that happens, we said, okay, we can take a qualitative approach. This is giving me the slope at any point xy that lies on the solution curve. If I know the slope at any point xy that lies on the solution curve, I can graph what's called a direction field. So at every point xy in some grid, I can draw a little line segment that has a slope given by this function. And we can do this for lots of points. And then we'll have a bunch of arrows on a grid that all have the same slope. And usually the vectors on this grid and this direction field are all scaled to have the same length. And then we can follow those arrows to graph a solution to the differential equation. Now, not every point xy in the xy plane is on the solution curve to the differential equation. But if we have the slope at every point xy given by this function on the right-hand side, and we know that the solution curve passes through this point, x naught, y naught, because we have this initial condition, then when we're at this location, we know the curve has the slope given by f of x naught, y naught. And then we can follow that arrow to a new location. And then there will be an arrow over there. And we know that that's supposed to be the appropriate slope. And we just keep following the arrows as x increases to infinity and as x decreases to potentially negative infinity. And we're able to graph the solution curve by plotting this point. Let's write this down. We can graph the solution curve by plotting x naught, y naught, and just following the arrows. Those arrows or vectors have the right slope because they were generated using this right-hand side of the differential equation. So when we do this, we're able to get a graph of that solution even when we can't write down the function y of x that satisfies that differential equation that passes through that point. Even when all of these methods fail, we can visualize a solution using a direction field. Euler's method is doing the same thing that we were just talking about with the direction field, but it's doing it numerically. Now I'm going to show you how to do Euler's method by hand to get approximations of the solution to this initial value problem by using this point and using the corresponding slope to find a new point and a new slope that should be on the curve, and then following that slope to get another point that should be on the curve, and so on. Now we're only going to do this for a few points. When a computer does this for you, when you have a numerical differential equation solver, it's using a method similar to Euler's method. It's not necessarily Euler's method, and it might not even be improved Euler's method, which is just a better numerical approximation of the solution of a differential equation. This is a pretty rough method in that there does tend to be a lot of error in the solution as you get farther and farther away from this initial location, x naught, y naught. But this is a good first introduction to numerical methods for solving differential equations. So when your computer is doing this, instead of just doing this for a number of points, which we're going to do for maybe 3 or 4 iterations of the method to get approximations to the solution, the computer is doing that a lot of times, and it's you doing that for very small step sizes. Okay, I think I'm getting a little bit ahead of myself. So let's talk about how we might find an approximation to the solution. Now this is telling me one thing. This part is telling me that we know that our solution curve passes through the point x naught, y naught. Now, if I am at this location and I know that my solution has a slope of f of x, y, well, then I know that the solution passes through x naught, y naught, and it has a slope of f of x naught, y naught at that location. With those two pieces of information, I can find the slope, or excuse me, I can find an approximation to the solution at a nearby point. You can call that nearby point x naught plus h, or if you prefer, you can call that x naught plus delta x. H and delta x are used interchangeably here, just kind of like they are in Calculus 1. Or we could just call this next x value x sub 1. X sub 0 is our first x value. X sub 1 is the next one after we take a tiny step size delta x. But we can approximate y, the solution to the differential equation at x1, just using the tangent line. Because I know that the tangent line passes through this point, and the tangent line has this slope. I can put those two pieces together to come up with the equation of the tangent line. So this is what we have. We know that the tangent line at x naught, y naught satisfies this. That's probably been a little while since pre-calculus, but this is called the point slope form of the equation of a line. Y minus y naught is equal to m times x minus x naught. And this is where m is the slope of the curve, or slope of the line, and x naught, y naught is a point on the curve, or point on the line, excuse me. It's just point slope form. But now here, x naught, y naught is given by that initial condition to the differential equation, and the slope is given by f of x naught, y naught. That's the right-hand side of that differential equation when we solve for the derivative. So that's my tangent line. Oops, that x naught shouldn't be there. Maybe my tangent line looks like this. Trying to get a straight edge here. There we go. Now that's the tangent line to the solution curve at x naught, y naught. And this is not a good approximation to the solution curve if we get too far away from x naught. But if we stay close to x naught, we can say at nearby location x1, y sub 1, where y sub 1 is on that tangent line, is a good approximation to the solution. So I'm going to call the y value at this new location y1. So we've got this, so we've got our tangent line, and we only want to use this for a tiny step size delta x. If I evaluate this at x1, y1, I get this. And then if I add that y naught to the other side, I get this. Now x sub 1 minus x naught, that's delta x. So I could write that this way. Okay, so let's think about what this says. This says that y sub 1, which is an approximation to the solution at x sub 1, is equal to the original y value plus the slope at the original x naught, y naught, slope at that location, times some change in x. Or change in x is the step size that we took to get from there to there. Okay, so we do that. And that gets you 1 point, and this is an approximation to the solution at x1. But now that I'm at this location, I've got an approximate or a new point on my solution curve, x1, y1. And once I'm at x1, y1, I can use the tangent line over here. So now at this new location, I've got this slope. Also given by the right-hand side of that differential equation. So y is y and x satisfy this equation. Y minus y1 is equal to the slope times x minus x1. And the slope is given by that right-hand side of the differential equation. Again, I don't want to use this all the time. This is only a good approximation to the solution curve if I'm near x1, y1. So I'm going to use this line to find an approximation of the solution curve at a nearby point, x2. So let's see. So y2, that's the approximation of the solution at x2, satisfies this equation. So if I add y1 to the other side, I get that, x2 minus x1. I could call that delta x, that'll be my step size. If I take the same step size from x naught to x1 as I take from x1 to x2, and so on, and so we get this. Do you see the pattern here? In general, what we're going to do is we're going to say that y sub n plus 1 is equal to the original y value, or the last y value, plus the slope at the last xy pair, and that slope is given by the right-hand side of the differential equation, times delta x. And x sub n plus 1 is equal to the last x value plus delta x. Or if you prefer, you can say it's equal to that first x value plus n times delta x. Because to get from x sub 0 to x sub 1, we added delta x once. And then to get to x sub 2, we add delta x again. And to get to x sub 3, we add delta x again. So to get to x sub n plus 1, we add delta x n times to that original one. So these are the equations that define our approximations to the solution. This is called Euler's method. And again, all it's doing is it's using that tangent line as an approximation to the solution at point after point after point. Now, the farther you get from that x naught, y naught, the worse this works. And there are better numerical approximations, but this is a good one to start, just using the tangent line. Now, forgot to write this here. Y sub n plus 1 is an approximation of the solution curve, or y sub n is an approximation of the solution curve at x sub n. Or in other words, if I know that x naught, y naught is on my solution curve, and then I take a little step delta x and I use that tangent line to approximate the solution at x1, well, then y sub 1 is an approximation to the solution at x sub 1. It's not necessarily equal to the solution at x sub 1. I wouldn't actually expect it to be equal to the solution at x sub 1, but it's a decent approximation. And then once we're there, we're going to create another tangent line. Maybe it's this. Maybe the slope has changed quite a bit. Maybe that's our slope this time, or that's our tangent line, because the slope is very different at this location. And then we'll take that same step size delta x. So this is x sub 0, that's x sub 1, this is x sub 2. And then we'll say, and now that y value there is our y sub 2. So what you end up doing is you start at x naught, y naught. You use the tangent line to find the solution at a nearby point, x1, to approximate the solution there. And then you use the tangent line at this location to find the solution at a nearby point, x2. Maybe that's our approximate solution, y sub 2. And then you do the same thing at x sub 3. Maybe the tangent line's negative, or has a negative slope this time, so we end up over here. And so that's y sub 3. And so you've got x sub 0, y sub 0, x sub 1, y sub 1, x sub 2, y sub 2, x sub 3, y sub 3. And if I connect these with line segments, that's an approximation to my solution curve. Now, if delta x is very small, and we do this a lot of times, we could get a very nice looking solution curve, a very nice looking approximation to the solution. So I hope you can see that this is the same thing as what we were doing with the direction fields. With direction fields, we started at this location and then we followed the arrows, which meant the arrows were indicating that slope. The slope of the arrow was given by that right-hand side of the differential equation. And then when we were at a new location, we followed the arrow to the next location. And then when we were at a new location, we followed the arrow to the next location. It's exactly what we did over here. Now we're just doing so numerically. Now you can tell that this is very tedious. And as again, there are some problems with accuracy. This is not necessarily the most accurate numerical method, but it's a good place to start. It's a good first numerical method. It's important that we are familiar with this so that we know how numerical methods work. We understand that numerical methods exist, but in practice, this is a very tedious way to find a solution to a differential equation. Okay, let's apply this. Let's actually solve an example problem now. All right, so here's our example problem. Let's see, you have dy dx equals 0.1 times the square root of y plus 0.4 times x squared. And you know that y of 2 is equal to 4. So you've got this IVP, and you want to apply Euler's method to solve it. Now, you might notice, if you were trying to use one of the methods that we've discussed previously, that this is not separable. It's not first order linear. It's not Bernoulli. Yeah, it's not Bernoulli because of that 0.4x squared term. Not homogeneous polar. and it's not exact. So none of the methods that we've studied previously will work. But we know that when x equals 2, y equals 4, that's on the solution curve. And we might be able to use this method, or we will use this method, to approximate y at 2.5. So maybe the problem statement says, use Euler's method with a step size of h, or delta x, equals 0.1. We want to use this to approximate the solution to the IVP at, let's say, 2.1, 2.2, 2.3, 2.4, and 2.5. Okay. So here are our formulas for Euler's method. Y sub n plus 1 is the last y value plus the slope at the last xy pair times delta x, or if you prefer, you can use h there, that's fine. And x sub n plus 1 is the last x value plus delta x, or alternatively, you can think of it as the first x value plus n times delta x. Okay. And with that in mind, let's find our first approximation. Now we were told that delta x equals 0.1, so I will write that down. And this tells me that y, or x naught, y naught, that point on the solution curve where we start is the point x equals 2, y equals 4. So when x is 2, y is 4, that's on the solution curve. We know that. And I know that when I'm at the location x equals 2, y equals 4, this right-hand side gives me the slope at that location. So this is our f of xy. That's slope, because that's what the derivative is. It's the slope. Okay, so if I want to apply this formula here, well, when n equals 1, or excuse me, when n equals 0, this is what we get. We have y sub 1 is equal to the original y value plus the slope at x naught, y naught, plus, or times delta x. Well, the original y value was 4. And then to find the slope, I'm going to evaluate this right-hand side of the differential equation at x equals 2, y equals 4. And then I'll multiply by my step size, delta x. Okay, I'm going to do this evaluation of that slope formula over here on the side. F of 2, 4 is this. We had 0.1 times the square root of y plus 0.4 times x squared. X is 2, y is 4. Square root of 4 is 2, so I've got 2 times 0.1, which is 0.2, and then you've got 0.4 times 4, which is 1.6, and when you add those together, you get a slope of 1.8 at that location. So you've got 4 plus 1.8 times delta x, and delta x is 0.1. So you've got 4 plus 0.18. So y sub 1 is 4.18. Now remember, this is an approximation to the solution at x sub 1, and x sub 1 is the original x value. That original x value was x equals 2, and then we're adding delta x to that. So this is an approximation of the solution at x naught plus delta x. So that's at x equals 2.1. Now this is not going to be to scale, but this is saying that at x equals 2.1, y is approximately 4.18. So there's 5 at 2.1. We want y to be 4.18. That's our next xy pair. So that's x naught, y naught, and that's x1, y1. Okay, now let's do it again. When n equals 1, we'll have y sub 2 is equal to the last y value plus the slope at that last xy pair times delta x. So again, all we did the first time was we found a tangent line here. And we took a little step size, delta x equals 0.1, to get from 2 to 2.1. And we said, well, if we take that little step size and we use the tangent line to approximate the solution, what should the solution be? And we said, well, according to our tangent line, y should be approximately equal to 4.18. Okay, so now we're at this location, x equals 2.1, y equals 4.18. And we want the new y value for the next step. So to find the new y value at x equals 2.2, so we're going to take one more step of delta x units again. I take the old y value, which is approximately, well, the y value at the last location, which is 4.18, and then we'll multiply by the slope at that location. X is 2.1, y is 4.18 at that location, and we multiply that by delta x. To find this slope, I will evaluate this expression over here. You've got 0.1 times the square root of y plus 0.4 times x squared. Now you're just substituting in 2.1 for x and 4.18 for y. And I get this decimal. And I will go out to the 5th decimal place. This is 1.96845 approximately. And we're multiplying that by 0.01, or 0.1, not 0.01. It's multiplying by a 10th, so it just moves the decimal over once. And then we add that to the last y value. 4.18 plus 0.196845, and we get approximately 4.3768. Now again, this is the approximation of the solution curve y at this new location, x sub 2. And x used to be 2.1. We took a step size delta x from there of delta x equals 0.1. So we go from 2.1 to 2.2. So we're saying when x is 2.2, y is approximately this 4.37. So at 2.2, y is 4.37. So maybe it's there. And I actually don't think I'm going to go all the way out to 2.5. So we have approximated the solution at x equals 2.1 here. And then we approximated the solution at x equals 2.2. Let's just go to 2.3. I don't think we need to go to all the way to 2.5. Let's just do one more iteration. At n equals 2, the new y value, or the new approximation to the solution curve, is equal to the y value at the last location plus the slope at the last location times delta x. And the y value at the last location is approximately 4.3768. And then we can find the slope at that location. The last x value was 2.2. The last y value was that 4.3768. You're going to multiply by delta x, and then you're going to add all of that together. So we'll do all of this over here. We'll evaluate our slope function at x equals 2.2, y equals 4.3768. So we have 0.1 times the square root of 4.3768 plus 0.4 times the x value of 2.2, and we're going to square that. Then we're adding 0.4 times 2.2 squared. And that gives us a slope of approximately 2.1452. Okay. So we take the old y value and then we add the slope, which is change in y over change in x. And then we multiply by change in x. And that gives us a new y value. It's the old y value plus the change in y. That's another way that you can think about this. Okay, if we add these together, this is what we get, approximately 4.59132. And this is an approximation to the solution curve at x equals 2.3. So just to make it a little bit easier to see, I'm going to imagine that we've zoomed way in. So at x equals 2, we're here, and at y equals 4, we're here. And then at 2.1, the y value was 4.18, approximately. And then at 2.2, we said that the y value was approximately 4.3768. So 4.38 approximately. And at 2.3, we said that the y value was approximately 4.59. And then if we connect these with line segments, that is an approximation of our solution curve at this location, this location, this location, and this location. So this is, again, very similar to taking that direction field and saying, if I'm at this location and the slope is given by the arrow in that direction field, follow the arrow to this location. Once you're at this location, the solution, there's an arrow there that tells you what the slope is. Follow the arrow to that location. Now, when you're at this location, there's a different arrow that tells you what the slope is. Follow that arrow to this location, and so on. That's exactly what we did with direction fields. We're just doing this numerically here. So that's how we use Euler's method to approximate solutions of a differential equation.